Sweet. We're going to dive right into our first session, or the first panel here. Sorry. So our first session is going to be is our high-level design abstractions type of thing. So we got like a bunch of papers about compilers and high-level tools for generating hardware. I think we're good. Yeah. I'll keep fiddling with this, but you go right ahead.
Yeah. Okay. So good morning, everyone, and also hi to everyone online. Today, I'm going to discuss our experience with MIR. Our experience is based on the development of Dynamatic, which is an open source HLS compiler for generating dynamically scheduled circuits from C code. What's special about it, it has better performance than conventional HLS tools for programs with irregular control or memory accesses. Therefore, a few other things I want to talk about. For instance, the research community really loved the tool, and we have seen over 30 papers published at top conferences and journals. Also, we have actively developing the tool, and in the past months, many PRs have been merged, and we opened and closed many issues. We also care a lot about reliability. In fact, every commit to the main branch is monitored by automatic regression tests and unit tests to prevent all sorts of problems. So what would you like to share with the LATTE community? First, I would like to talk about the benefits of MIR that we see. Well, building Dynamatic is very challenging because it is a compiler, and I believe that the audience knows how complicated it is to build a compiler. Second, it is an open source tool, so we have to think very hard into how to integrate and collaborate with external projects. Furthermore, we live in the academia environment, which means many of us are students, and we don't know very good software engineering practices. But MIR actually helps us to elevate all these issues. For instance, MIR is the infrastructure for building new compilers. It allows MIR-based frameworks to easily reuse each other's code. And also, it is built by professionals, which means it contains good software engineering practices that we can borrow. So what could be more interesting for the community is perhaps the issues that we identified. So first issue is MIR a good fit for encoding graphs? Well, let's see the use case in Dynamatic. Here, we want to record some profiling information to identify which parts should be optimized more than the other parts. In this example, we have a control flow graph that we want to record the fact that we go to the then block from the entry block in most of the time. So let's see how we can encode this particular information into MIR. So for those of you who know the syntax, this is the syntax, but I want to highlight two key challenges. First is in between basic blocks, you basically cannot have any values. So this is just how the language works. And second, even there would have been a value, we cannot put any sort of annotation on this. So as a result, we have to rely on somewhat a very hacky workaround to deal with this issue. So although MIR has promised us, but is project integration and collaboration become easy now? Let's see a concrete example. Here we have two repos with two different dialects and two different MIR versions. And our goal is to enable collaboration, so we copy the dialect definition and we write some conversion paths. But the problem is this will not work out because the integration will fail due to the mismatch of MIR versions. And we came across this when we tried to integrate the Google XLS tool, and we discovered that, well, the collaboration worked really well, so we had very great discussions, but the resulting product is not so maintainable due to this problem because they basically update their MIR every day, and we do this once every 2 years. And the third problem is, do we have a mature enough MIR-based C frontend to encourage new tools to build new HLS tools? So to give you some context, what do we mean by an HLS frontend? Well, the goal of HLS frontend is to convert C code into IR. It performs all sorts of canonicalizations and optimization. The problem is many crucial IR optimizations are not there. It might be surprising because we build so much things into MIR. How come that we don't have them? To give you some examples, we have ins combined and simplified CFG as so these super complicated LBM passes that are larger than the code base of Dynamatic itself. We want to get benefit from them, but we cannot maintain them because it's still complicated. So as a result, if you look at our compiler pipeline, you will see that in the end, we reintroduced LBM to our pipeline to ensure that we have a competitive quality IR. So which is something that we aimed to avoid at the first place when we first moved to MIR 3 years ago. So I believe that many of our observations generalize beyond HLS. So suppose that you take away the quantifiers, I believe that many of the problems still apply. So in a more severe or maybe less severe degree. And our hope is that we can bring this awareness to the community so we can think about these solutions. So I would like to thank you very much for your attention, and please give a star if you like the topic.
That was very cool. So keep in mind all your MLAR and circuit questions for the panel when they come up. Our next speaker is Amelia Dobis. Please take it away.
Wonderful. Hi, so I'm Amelia. I'm here with my co-author who's sitting right there in the front, Gongxi. And we're going to talk to you, I'm going to talk to you, I guess, about how you can encode purely functional languages in an RTL-based compiler. So first, let me talk to you about Circuit a little bit. So Circuit is, as you can see here, kind of a unified compiler. It can handle a bunch of front ends, and then it kind of lowers everything to a unified IR. And what you can notice about these front ends is that they're all kind of RTL focused. So it's either like RTL or like HLSE things. It doesn't really handle many higher level paradigms natively inside of the compiler. And so that comes to the question, okay, how do we support something like Clash? So what is Clash? Clash is a Haskell as a hardware language, which means it's literally just Haskell code that gets reinterpreted to produce a netlist. So it's not quite HLS, it's not quite a DSL, but it's still like a purely functional language that we want to support in our compiler. This can produce VHDL or system Verilog, and it has its own sort of Haskell-based EDA infrastructure, but it's not very unified with the rest of sort of the open source ecosystem. So how can we make that a bit better? So first, this is what Clash looks like. As I mentioned, just Haskell. So here we can see kind of like a finite state machine being declared as like using an ADT and pattern matching. So this is a really neat abstraction to have, and we would want to kind of utilize this in Circuit to support languages like this. So our goal is to modernize Clash by basically porting it to Circuit. So this is kind of the high-level infrastructure we had for porting Circuit. So we have for porting Clash to Circuit. So we first have our Clash code on the left, which then uses the GHC compiler to produce systemfc. And then we basically identified 3 entry points that we could use to port this to Circuit. So our first entry point would be basically taking the output of Clash, which is our net list, they call it at the end, but it's just basically system Verilog, and feed that into the Circuit's Verilog frontend. And then we could somehow get benefits out of that. The second approach would be to go from its normal form. So that's one big thing that the Clash compiler does is once it reaches systemfc, it will then kind of flatten and elaborate everything into this normal form that is basically kind of like a giant SSA, like a giant SSA program that looks very similar to RTL. And so we could basically pipe that in directly to the core dialects because the abstraction level is very similar between the two. And then our third approach would be to try to retain all of that high-level information we have in our source code and basically just like connect systemfc directly to Circuit. And so that would require the introduction of new abstractions in Circuit. So let's talk about this first approach for a second. So the idea is to run the full Clash pipeline, which yields the system Verilog, and then to use a Circuit's Verilog frontend, which is powered by the LHD pipeline. And this would allow us, so the main sort of benefits of this is that there's like absolutely no engineering effort, but it still allows us to use all of Circuit's optimizations and get kind of their high-level, high-quality backends with very minimal effort. So now if we move to this second approach, which is, so the first approach is kind of the very naive approach. The second approach, maybe we can get some better benefits out of it. So the main takeaway from this is that if we don't go through system Verilog, now we no longer have all of these kind of opinionated features that system Verilog has. So there's certain transformations and lowerings that Clash has to do to fit the system Verilog's model. Maybe we don't have to do that and then extract better optimizations out of that. But the problem is this still does not retain the high-level structure of our source code. So now we come to our final approach, which is basically we have to introduce a specialty dialect into Circuits that allows us to encode all of these like functional components. So I'm going to quickly walk you through an example. So we have our example from before. It's a finite state machine. So how do we encode each part? So we can encode sort of general computation. So the specialty dialect we're introducing is called the LC dialect for lambda calculus. And so it can support lambdas here, like we can see here, with our like general computation. and it can support ADTs. So now we can encode this ADT in Haskell using our LC dialect. And now we can sort of handle pattern matching also within our dialect. And so now what we can see is that we're retaining all of this information that we had, all the information, sorry, that we had in our front end. We can now utilize it as well during compilation. And so we can do that for every single case. And then the idea is that at the very end, one big lift that Clash does is it has this melee function, which basically does a recursive value binding and is kind of sort of its way of saying this is a finite state machine. So it takes the outputs of the lambda and then feeds them back in as inputs. And so we kind of encode that recursive pattern directly in our IR as well. And so what does this enable us to do? This basically allows us to retain all of the high-level structure, which can enable us to identify things like finite state machines, do sort of better optimizations that I can talk about during the panel if you have questions about it, and sort of analyze the functional structure in order to do kind of more difficult tasks that might be hard to do otherwise. And I see that I've gone slightly over time. So here's sort of a bit, I'm going to end with like an opening discussion for later. So the idea here was to add sort of more support for non-RTL paradigms to an RTL-based compiler. And the idea is, can we expand this to sort of other paradigms, potentially message passing paradigms or things like that? Yeah, thank you. Thanks, everybody.
Great. We have one last speaker in this high-level design abstraction thing. Amelia, would you mind stopping sharing your screen? Cool. And it's Jonathan Balkand from UC Santa Barbara.
Hi, folks. Can you hear me in the room?
Yeah, we can hear you pretty good.
Great. Sorry I can't be there. Always love LATTE, so I'm glad to participate today. This past fall, the university let me loose with the sabbatical quarter, and I had a lot of fun working with Claude. So I have come up with this tool, this framework called IsoComp. What is this? IsoComp is kind of a new way to design processors. We are used to either using HDL or RTL or HLS, and these kind of are some kind of spectrum between control and automation. This is something different, I think. IsoComp is a system where you start from isospecs. You write a spec per instruction. It's a tiny program. Ideally, any of you in the room could write a program that looks like this on the right. Claude can also write these programs, and lots of them. You can then extract these isospecs per instruction into a single cycle machine in a graph IR that I call a resource graph. And a single cycle machine here is something that unrolls all of the intra-instruction parallelism. So you have this insane, theoretically extremely high performance machine, but in practice, it's complete garbage. So how do you make it not be garbage anymore? You perform iterative optimizations. And when I say you perform iterative optimizations, I mean you as the designer guide the flow. At the end, you can then output HDL code. Somehow I have 9 backends. Again, Claude is an absolute beast. In this system, optimizations become algorithms. So we're able to decouple the what, the where, and the how. We have a large catalog of possible algorithms. I'll talk about those. The designer points where they should happen in the design, and then the algorithm represents the how of what's going to happen. The question is, does this actually work? Can we even extract machines from the isospecs? The answer is yes. I have more than 22 different specs for a bunch of different ISAs that you have and have not heard of. If anyone's heard of all of them, then you should send me an email because I would love to ask how the hell. These can be as small as one file. So in the case of Subleak, it is a one instruction set computer. And then you have something like I-486, which has thousands of instructions. Weirdly, this DSL that I use doesn't really have any concept of like conventions of how to define machines. So you can actually represent all these weird machines, purely functional machines, CISC machines, one instruction set computers, etc. And you can also importantly represent things like I/O interrupts, ports, etc. What does this give us? We can actually boot Linux in Verilator simulation on 10 of the single cycle machines built from the isospecs. That's not really useful. We need to be able to optimize these. So here is a list of optimizations that we have built inside the system. And the designer is going to just be going through a process of choosing those optimizations from the catalog, providing specific input for those optimizations, like do this here. What are the nodes I want to use? Where do I want to put the pipeline cuts? How should I resolve the hazards? These kinds of things. This means that every machine is just an instance of a Python script that refines from the initial single cycle machine, which is pretty interesting. You can write a script that's highly parameterized, number of stages, etc., whatever it is. And so ideally, then you can take your single cycle machine, which boots Linux, add pipelining, add caches, add TLBs and page table walkers, and then that thing should still boot Linux. And I have a demo of that, no, not to show, but I have a demo where I can do that for RISC-V. Some potential questions I would love to chat with people about in general. What other designs could we create with this flow? What kinds of accelerators, other things? Inspired by Andrew Alex, who's here, I was able to ingress and egress AES and SHA accelerators from ILA. Can we represent other kinds of machines? VLIW is one that I've been having a hard time figuring out how to make it work internally. What other abstractions could be introduced? As I say, I don't really have a ton of abstractions here. If you look at ILA, you look at SAIL, they have models of like fetch and decode and execute, and this thing's just a big bag of semantics. I've been taking advantage of aspect-oriented programming, which is super weird because no one has ever taken advantage of aspect-oriented programming. I also have this concept of an orthogon for orthogonal ISAs, which is some term that they invented decades ago that we don't use anymore. I want to know like which kinds of optimizations may be difficult to incorporate into the system, and also could we like cross-pollinate between CPUs and other kinds of optimizations that we apply in general. Also, kind of this question about like, yeah, how do we integrate with other compiler infrastructures is definitely one that is heavily on my mind. As I mentioned, basically 100% of this code is written by Claude. That is, I looked at the repo yesterday and it said something about millions of lines of code. There's about 600,000 lines of code in the repo. This is thanks to a Claude subscription generously provided by Anthropic. I will leave it here and we can move on to our panels. Thanks.
Thanks, Jonathan, and thanks to our three panelists. So we're now going to move into the round table, which is hilarious because they're very rectangular tables. But anyway, so we're going to do the same rows that had to turn around their chairs last time. Do it again, please. And we're going to make either one or two small groups per like pair of tables here. And remember, the point is to like, discuss stuff, but also distill questions to kind of like point you at the big themes. Some themes that I saw were program representations, that is like intermediate languages and stuff, concretely MLIR things. Also kind of the question about like how to represent the optimizations, that is like where those come from and how to write them. Anyway, it's up to you to decide what you think the big high level themes are. Please try to, think broadly about questions you might ask and put them on Matrix. It is now 9:47, which means you have run out of time to come up with good questions, and now is the time to answer these questions. So please wrap it up and turn your chairs back around to point them at our panel here. I trust that momentarily our Zoom people will be coming back into the main room and we'll also have Jonathan here. Yes, great. Okay, cool. Jonathan's on our panel and we have our two in-person panelists here. Imagine taking Jonathan's face and putting it right here on the panel. The point is that we now have questions that are sort of directed at this entire panel. So like this is meant to be answered by any of the three of you. Because there's some common themes here. A bunch of cool questions here on Matrix. It is not too late for you to keep typing questions. I'm going to keep watching here. First one I ask comes from Franz, who's asking about MLIR and circuit and stuff. He's sort of asking the question like, kind of where does it end with the proliferation of dialects? It's sort of related to a question that I asked too, which is like, like where are the gaps? Do we have enough dialects? Do we have enough transformations? From your perspective, having used circuit and MLIR, like where are we at? Are we in danger of having too much fragmentation among too many different dialects? Do we not have enough? I don't know. What's y'all's opinion?
Yeah, so I guess this is kind of assuming that dialects are isolated blocks that don't necessarily interact. But the main idea is to not really create this sea of disparate dialects that all kind of work in their little corners, that just in general in MLIR fashion is to have like things interoperate. And so when we're adding new dialects like the lambda calculus dialect, the idea is more like, okay, we have this gap in what we can sort of encode natively and sort of what analysis we can do. How can we add sort of just the components we need to encode this high level information while also interoperating with existing things? So it's more of like growing our space of of representation rather than creating sort of disparate satellite ones. I guess I don't know that. Yeah. Work on that.
So I guess when we moved from LBM to MIR, the idea is we kind of moved from like a universal dialect to N by N problem, right? Because yeah, the most complicated situation is you have N different dialects. Everyone has a conversion to the other dialects. So in some sense, we use Amelia, which is like you have to define your string. So in such a way that you have a manageable set of things that you're working, so you don't run into explosion. It's you also.
Yeah. Yeah, I think this the explosion of dialects isn't necessarily a problem. It's more like making sure, yeah, as mentioned, that you're using only what you need and not just like random other dialects just because you can.
By asking the questions here, I don't mean to foreclose follow-up questions. So if that sparks anything for anyone, please just raise your hand and I will call on you. That includes folks on Zoom. You can virtually raise your hand. Yeah, do you want to ask, if you don't mind just like talking loud. Actually, wait a second. We have another microphone. Can you talk into this microphone?
So I'm working on the middle end compiler that use a lot of ML dialects for designing the dialects. So in my experience, what I'm observing is people are free to write all different dialects and definitions, semantics. But then I sometimes got confused because every new dialect comes out, and then they also seems like have a different abstraction level. But in ML itself, operation is also next definition of operations. So is that a good way that I'm not sure that this is part of my limited experience over here. Like it seems like the abstraction levels kind of getting intertwined each other. It's a little bit messy for me.
So I don't know if I got the question part. You're saying like it gets a bit messy once you start interleaving sort of abstraction levels.
Yeah.
Sort of how do we manage?
Yeah. So there are so many dialogues, and then they are all allowed to exist in one area.
Yeah.
But then when you do dialogue conversion,
Yeah.
You might change some dialogue, and then the IR might sometimes you have a high level or low level, all mixed up.
Right. So again, like the idea is to really focus on what problem you're trying to solve in that particular case. So it's like if you want, so you can do these like dialect conversions and then kind of lower the abstraction level incrementally. But the way I like to do it is once you enter you start out in kind of a high level that's maybe close to your source code, and then you kind of exploit that to do all of these more, I guess, global analyses that are more difficult to do when you're at a lower level. And then once you're done with all of those optimizations that are really specific to that high level, then you kind of try to lower everything. So you're still trying to guide things in such a way in your lowering pipeline, because you can sort of define these custom pipelines in your tools in MLR. So the idea is like to kind of guide things in such a way that you're lowering incrementally until you reach maybe your kind of target, which in our case most of the time is like the core IR, like the core elements. I don't know if that answers your.
Yeah, I'll follow up.
Yeah. Okay.
Okay.
So the question I have is kind of related to defining semantics for MLIR dialects. So I think there's like two approaches to like adding dialects. You can either have like this quick turnaround time where you can add dialects, maybe at different abstraction levels, or you can go a little slower where you kind of restrict the amount of dialects, but you actually define semantics for them that are more formal, right? So question is like, which approach is more useful for hardware design?
I've heard to say, could question askers please identify their name and affiliation?
Oh yeah, so I'm Al Boris from Rutgers University.
Oh.
Yeah.
Yeah, so I guess for us, we kind of always go into the second direction, which is we have one single dialect always, and we hope that we have a super well-defined semantics and everything. So because let's say this is kind of easier for correctness, and maybe you don't lose too much in performance and so on. I don't know.
Yeah, well, I've mostly seen what's done in practice, and what's done in practice is just kind of rapid fire dialects that fit your particular goal. And then I spent a lot of time trying to formalize particularly the kind of the thing that everyone kind of funnels into. So in circuit, everything funnels into the core dialects. So I was like, okay, maybe that should be formalized. And then everything else is kind of like, as long as it has like a clear lower into that, then maybe you can kind of figure out your semantics from that. But I think that it is important to have sort of formal semantics for your dialects. In practice, I know that people don't do it.
When your semantics are defined by translation to a different dialect, is that called denotational semantics? Sorry, that was a joke. I want to say,
Denotation semantics.
I want to ask another question. There's so many good questions on matrix. Awesome work, everybody. I want to ask a question that's like primarily relevant to the ISA conf talk. Julian asked a super interesting question about like the sort of notion of like, you know, so like if the idea is gradually lower from a really bad processor into an actual viable processor, is there any sense in which you can get kind of like good feedback along the way? That is to sort of know, like, I did this pipelining strategy, even though I'm not all the way to a good CPU, can I tell, like, am I headed in the right direction? And I think this is sort of like generally relevant to the question about like how to get kind of like, you know, how to get feedback about the quality of a design before you're all the way to RTL and then all the way through to EDA flow to get feedback and stuff. So I'd like to start with Jonathan, but this is relevant to y'all as well.
Yeah, I mean, there's something that kind of I thought about in the abstract, but maybe not specifically before. I actually, you know, because we can just generate HDL code out the back, it should be pretty easy to just, you know, go and throw that actually at the tools and just see what they give us back out, or you know, I don't know, call cacti and get an area estimate for the memories that are in there, or a timing estimate for the memories in there. And so I think that this should be pretty easy to integrate, and that like the HDL is just an artifact that you produce, and then you could throw it at the tools and see. I hadn't really thought about having this in the iterative flow in the beginning necessarily. But I really like the idea. I think it'd be really cool to have that. So I'll try and prototype with that sometime soon. Yeah.
Cool. You got any thoughts about like how to sort of like, you know, get feedback on optimizations in the MLIR ecosystem? Like, is there any sense in which people are doing that as opposed to like, you know, export the Verilog and then get feedback from EDA toolchain?
Yeah, so actually it's kind of related to one of our research domains in our group. So the idea is we want to predict like the resource cost and also the latency of a particular HRS design, probably from C code. And the way that we did it is kind of to train like a GNN for our design. So like kind of for different flows, you train your domain specific models to be able to have this kind of quick feedback to the upwards kind of design space exploration. So if you're interested, please check out our group page also.
Do you have
I mean, when it comes to like optimizations, I feel like it's almost a bit difficult to get intermediate feedback. The approach we've been taking has mostly been going through backends, but then again, you have to take into account, like we just run individual optimizations and then run them through like a system that like downstream tools to get feedback. But for verification, you can get lots of feedback because you know you can just immediately report things like at these intermediate levels, but for like more design related optimizations, it's a bit trickier.
Totally. I got a bit of a left turn question to ask here, which just comes from Rosa's group, which is about the sort of like about kind of like methodology questions. That is, like we sort of have two different like extremes of like styles of research prototyping here. Maybe as like in some ways like building something into MLIR and even hoping to keep up with the MLIR treadmill is sort of like, let's try to build something real-ish that maybe people would actually use. No offense, Jonathan, sorry, but like, you know, like the sort of opposite approach.
People are going to be using this soon, Adrian. Don't worry.
Great. Like let's build something big and end-to-end impressive and sort of like it gets an early stage result, but it's not sort of like, you know, like sort of built into the MLIR ecosystem in a way that it's the same. So I guess I'm just curious if anyone has thoughts about like the trade-offs between those two approaches.
I I mean, I have, I guess, the thoughts, but it's more of like, you can try to jump into MLIR sort of for everything you do, but it does have a very high kind of engineering overhead. So it's not free to do these things. But it does, and they're also like, it's not just like you can build it into MLIR, but it's also like, do you want it to be upstream into like a larger project, like upstreaming into circuit or something? People then will have very strong opinions about the code, and it might take weeks to get your sort of PR merged when you could have already have like moved on type of things at that point. So there is always that kind of trade-off. But then once it's in, you then kind of have people naturally start using it just because it's there. I've noticed that with like the VTOR back that I added to the circuit, which I thought was just useful for like a small thing, but then not lots of people are contributing to it just because it's there. So there's also that aspect of, I guess, dog food in a sense.
Totally. So, like in my opinion, this like this huge project that's like circuit and dynamatic are more like a compromise of a million different things. It's not like they're to show a particular insight, but it's like a foundation for other experiments. And to this, in this sense, we shouldn't kind of judge smaller works or more experimental works because they actually want to show a particular point, right? So they serve fundamentally different purposes. So that's go ahead.
Jonathan, you feel like adding anything to that general thing?
I actually didn't hear the whole question. My audio
The
seems to be
question
busted.
is basically asking the question about like, should we be building kind of like robust like engineered systems, or should we be building like standalone prototypes?
Yeah, I kind of yeah, for a lot of purposes, I do think that there's something that we haven't thought enough about in terms of, could we be building robust designs that could last 100 years, right? Like, are there actually decisions that we can make today that are like, or designs that we could come up with today that will stick around, right? Like, are we still going to be seeing things that look a lot like Google's TPU in 100 years, right? And from that perspective, I think you don't know what your thing is going to turn into, and I think both directions are like super fruitful for us in terms of research. But I think in terms of practical realization, like maybe these things like rocket and such, could sit around and last for a really long time. And we should also be thinking about that long-term impact, not just, the immediate realization of what we can get. Yeah.
There's certainly like guesswork involved. Like, who knows which random research prototype is going to turn to a real thing. Rachel, you're about to say it's coffee break?
No, I was going to follow it,
Great.
but I guess maybe not.
Go for it. I'm going to make everyone sit and listen to Rachel's question.
I think there's also a follow-up here about like sometimes we architect things just to learn how they should be built, and in that process we develop research ideas, right? So one reason to build maybe things in LATTE is just to understand what trade-offs you have to make, to your point, to build a real system, right? And so I think there's a question about how we lose that if we don't do that coding part ourselves, and that's a question for you. And the other one is also a reliability question, which is it's a lot of lines of code, and how do you know it's correct? I guess I would just be scared if I saw a million line code base that I like didn't review myself or have strong confidence that it's correct. And maybe there's some like formal verification or other kinds of mechanisms you're thinking of to make that system have more reliability and confidence. Because I think that confidence question feeds back into like, what does it take to build a real system, and there are trade-offs involved.
I'm going to ask for a quick answer from Jonathan. We'll move on to a break here. Did you get that, Jonathan? I can repeat the gist.
No, I actually didn't. Sorry. Yeah.
The gist is like, how do you gain confidence in the correctness of your system when there's a lot of lines of code like that? Do you want to do a formal verification thing?
Yeah, I mean, I think ideally you take this prototype and you build something new where you can actually verify these things from the start. If you can prototype this thing in Python, then you can probably also go and prototype something similar in Lean and then have a lot more confidence in the optimizations in the code base and so on. And I think that's like a fruitful direction to be considering is like, if these things are more simple than we were giving them credit, then like maybe we can just formalize them and know that things should be correct. But I think ultimately it still comes back to the designer doing the right thing in the first place. So, what exactly some of those optimizations mean might be, or correctness criteria might be very specific in weird ways. Yeah.
Great. So it's just all move to lean. So that does it for our first session. Can we have a round of applause for our first set of panelists?